Welcome to part two for section 4. We're going to be hitting on basis now. And in the previous video, it definitely went a lot longer than I originally thought I'd know the time, but I knew it was going on forever. So I apologize for that. This is going to be much shorter, I promise. Is that they lead us to the definition for a basis. So we needed to talk about linearly independence, and we needed to talk about what it meant to be spanning, because the basis for a vector space is a sequence of vectors that are linearly independent and they span that space. So for example, let's say that we want to name the vector space R3. The vector space R3. If I want to come up with the basis for this, I need to come up with a sequence of vectors, so a set of vectors that aren't dependent on one another, so none of them are combinations of each other, and every vector, every point in this space can be gotten to through those sequence of vectors. In this case, we're going to need 3. Because if I want to be able to get to this entirety of the space, then I need just the right number of independent vectors. And so you'll kind of notice this is like the Goldilocks number needed to create and describe whatever space that we want to focus on. So for example, the most basic basis for this space would be using the 3 identity vectors, the elementary vectors. That is the standard basis for this. So if I take the identity matrix, which would be 1, 0, 0, 0, 1, 0, 0, 0, 1, if I take the columns of this, and that's the sequence that we're looking at, so 1, 0, 0, I'm really struggling with my zeros and ones, 0, 1, 0, and 0, 0, 1, this sequence of vectors are all linearly independent. The only way to get to the 0 is the 0 vector, so the null space only contains it. None of them are combinations of each other. And every vector that is in this space is a combination of these 3. And again, you can choose any random vector in this space, 3, negative 1,000, and then 1.2. And I can get to this vector by doing a combination of these. And so taking these 3 vectors, we call this a basis. And again, math not getting too fancy in terms of how we're defining things, it kind of makes sense if you think about just the word basis means, or how similar it is to the word of basic. It's what we boil this space down to in terms of its building blocks. And again, when I'm looking at this entirety of R3, I have these 3 vectors, but these aren't the only 3 vectors that we could take. For example, it is possible to still get to this vector if I was to choose 3 vectors like 1, 0, 0, but then maybe this next one I did 1, 1, 0, so not a scalar multiple. And then this last one, maybe we did something like, and here we've got to be careful, but what if we did something like 1, 0, 1? So if we had something like this, notice upper triangular, these 3 vectors are different. They're linearly independent, at least I hope so. If we were to look at the combinations, it looks like we've got a pivot in every column, so I think we're good, right? So I have another set of vectors that are literally independent that I can find a solution to this if I set it up, meaning I could describe everything in this space. This is another basis. And so one of the big takeaways that I want you to have just from this point is that bases are not unique in describing a space. We can actually find a lot of different bases to describe different spaces. And when we're solving problems, you don't have to find all possibilities, but just know that there's not just one answer. Especially when we're looking at spaces that are as grand as all of our 3 or all of our n. The takeaway is that if I have these three vectors, if I was to add one more vector in, like in the example that we looked at from the practice problems, so something like 2, 4, 1, I know that this is too many vectors. This would not be a basis if I was to take all of these. I don't have a basis now for R3. They're not independent. They wouldn't span, I mean, even though it spans all of R3, this vector's too much. It's not the Goldilocks number. And so that's why we have that free parameter. So when we're looking at defining a basis, remember we have those two components. We're looking for linearly independence and we're looking for spanning the space. So not unique. Now, that means that when I'm looking at a matrix, if my matrix is invertible, that implies if A is invertible, so not singular, then A is full rank, full column rank. And if A is full column rank, that means we've got pivots in every column. The columns are all linearly independent. That means the column space forms a basis for all of Rn, if this is an n by n invertible matrix. So I'll just kind of say if A is n by n. So this is one of the facts that's being stated. We kind of saw it when we looked at the three vectors earlier. At a full column rank matrix, meaning when I look at the combinations of its columns, we've got a basis for all of Rn. Now the second that we added one more, we're no longer looking at the column space. It kind of breaks this because now we don't have an invertible matrix, so it's rectangular. And so notice how this is also in reference to a square matrix, which is really, really important. So then what happens if we're looking at a matrix and it's not invertible? Then what are we finding and what are we looking at? And he gives an example here as a matrix for B that is singular, so that's not invertible. 1, 1, 1, 0, 1, 1, and then 1, 2, 2. So you can kind of quickly see how this is a combination of these two. So if I was to take this matrix and put it into reduced row echelon form, so essentially taking it to R0 is kind of our idea. Zeroing out, I'll write out my steps here. Row 2 minus row 1. So just taking this from the beginning, and then row 3 minus row 1. First row staying the same. Subtract, 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 subtract. We've got our row of zeros. Here are my pivots. Here are my free parameters. So what we've discovered based off of our prior work when talking about null space and things like that is that the first two columns of B are linearly independent, but the third is not. This verifies that if I add the first two columns together, it gives me this one. We see that combination already, but just for practice. And so if I was to only take the linearly independent, so if I cut the excess off, we're now not looking at every combination of my columns of B. We're only focusing on the linearly independent columns of B. We're focusing on the column space of B. Well, that's now no longer all of R3 because we don't have enough vectors to cover all of R3. This is covering or spanning a plane in R3. And it's not even spanning all of R2, right? It's just some sheet of paper in three-dimensional space, some combinations, and every combinations of those two vectors. But if I was to take that set of those two vectors, 1, 1, 1, comma, 0, 1, 1, we now have formed a basis for this column space. So whatever space, that subspace that we're creating here in R3, by taking the span of these linearly independent columns, we now have a basis. And remember that this is only one way to get every vector that is in this column space of B. That's what this is essentially representing. So a basis, again, is really just the name for taking the span of these independent columns or independent vectors, and it's the most basic vectors required to get everywhere in that space. And again, I think it can be semi-misleading to say basic because it almost implies it's the simplest vectors, which may not be the case. I mean, I think that you could argue these are all ones, which is pretty straightforward, but it's just kind of how I like to visualize and think about that word basis. I can take just these two and I can go anywhere I want to in that column space and get there. And so I think one more important statement just to really emphasize is that when we're describing a basis, is that every vector in that space, we can get there through one unique combination of the basis vectors, whatever basis we have. But that vector, there's one combination of these vectors, or if I found another basis, there's one unique combination here, or if I found another basis, there's one unique combination here. That always takes me to that one location. So basis is not unique, but to get to that solution, that vector in the space, there's always a unique solution. So it's kind of the squares, rectangles kind of statement. And now when we're thinking about this, where we'll kind of leave off and where this kind of leads into the final part of this 3.4 section, is that if I had a list of independent vectors, so again, if I'm taking these, for example, remember how this does not create all of R3? It's spanning a plane in R3 because there's only two columns. What if we could extend it? Now, no longer talking about the column space of B, but what if we extended it by finding that last vector that's needed to get us all of R3? Then we could do that. And so notice that this list of independent vectors is not enough, but I can extend it so that it would be enough to cover not the plane, but all of R3. And that's the first line that he says, that every set of independent vectors can be extended to a basis, versus every spanning set of vectors can be reduced to a basis. In the example, if I was to take these three, so 1, 1, 1, 0, 1, 1, and 1, 2, 2. If I was to look at every combination of these three vectors, we're looking at the span. But that span isn't linearly independent. But if I remove this vector, even though that vector kept me in the same space, if I remove it, we now have formed a basis. Because remember, adding this third column, it's just a multiple of these. So it doesn't take us anywhere new. It keeps us in that plane. It keeps us in the column space. But we didn't have a basis if I included it. By removing it, we now have a basis. And so that's what he's talking about when he's saying that every spanning set can be trimmed down, and every limited independent set can always be extended. Now, the first part references extended to a basis, and I think about it in terms of R3, R4, etc. The spanning would cut it down to form a basis for the column space or row space, or potentially all of R3, depending on what we're trimming down. So just a couple things. Now here again, we trimmed it down, but it didn't form all of R3. And there's, again, a couple of examples around that. So biggest thing, kind of final thing, it's the last thing at the bottom of 119 in the end of this video. The number of vectors in any and every basis is the dimension of that space. So in this example here, if I wanted to talk about the dimension of the column space of B, the dimension of the column space of B is equal to 2. It's the number of vectors that we have in that basis. So the basis will always tell me that dimension. And it doesn't matter if I use this basis for the column space, or if I was to find another set of independent vectors that gave me this column space. So again, if I if I performed that reduced row echelon form, that would also keep me here, or going through the reduced form. I would only need 2 vectors to get there. So remember, bases aren't unique, but the bases all have to have the same size. And that's where we're going to kind of leave off, because in the last part, and what he gets into in the book, is then proving that statement. And that's also kind of the last key idea when we start talking about subspaces, is that the dimension for every basis for a space in subspace is always the same. So they're not unique, but the number of vectors needed is always the same. Thus, the whole Goldilocks idea. All right, so hopefully that makes a little bit more sense with bases. Take a look at practice problems. Let me know if you have questions. And hopefully this example and kind of talking through it kind of helps.